All right. Hey, y'all. How you guys doing? Hope you all had a good break. Welcome back. Hope you guys are staying safe, found something to do at home, and let's get back to work. All right. We are in quarter four. So, yeah, it's good to be back. I missed you guys. It's been a while. So, if you looked on Google Classroom, I think I posted something April 8th about how grading is going to work for the fourth quarter. So the gist of it is that 40% homework, 60% tests or assessments or quizzes. And just make sure you're getting your homeworks in on time, which all of you are. So just keep that up and you guys are going to be fine for the fourth quarter. All right, so we are pretty much done with trig. I'll post some review questions on the homework, but we're starting a new topic today. And we're going to be doing area. So some of this is review, some of this is new, but we're going to be talking about the scaling principle for area today. All right, so the warm-up is a really simple one. Let me lead you through one example, and you guys can pause the video and try the rest. But let's take a look at this rectangle of 5 by 2 centimeters. What happens to the area when it is scaled by a factor of 2? So our original side lengths, let's say we have a length of 5 and a width of 2. The area, of course, is going to be 10. If you want to include units, centimeters squared. So when I scale it by a factor of 2, if I dilate by scale factor of 2, right, my length will become 10, my width will become 4, and my area becomes 40 square centimeters. And my length had a scale factor of 2, my width had a scale factor of 2. And what was the scale factor for the area? Well, we went from 10 to 40, so that experienced a scale factor of 4. All right, so take a minute. This should be pretty quick. Fill in the rest of these tables, and let's come up with a general principle when we're scaling by some factor. All right, so hopefully you finished that. And let's take a look. It should look something like this. All right, it's going to be 5, 2, and 10 for all of them on the first one. That's our original rectangle. When we scale by a factor of 5, the length becomes 25, width becomes 10, area is 250. All right, we scaled by 5, and it looks like the areas got multiplied by a factor of 25. When we scaled by a half, right, our area became 2.5 or 5 halves, and that was a scale factor of a quarter for the area when we scaled by a half in the length and a half in the width. So in general, what happens when we scale by a factor of r? Well, I'm starting with lengths of 5 and 2. Area is 10. If I scale by a factor of r, my new length is going to be 5r. Right? R could be bigger than 1 or less than 1. It doesn't matter. Right? My new width is going to be 2 times the scale factor r. And so my area is 5r times 2r. It's 10r squared. So when I scale by a factor of r, well, the area experiences a scale factor of r squared. So that's our scaling principle for area, right? We did the same thing with triangles a while back, right? It's true for any shape. We did it for a rectangle. We could have done it for a pentagon, any quadrilateral. A triangle works, a circle works, any shape, right? If you scale it so it's similar, right? Area of the similar scaled figure is going to be the original area times r squared, right? And r, of course, is the scale factor. So what we are doing in this warm-up here is, well, we are really doing a dilation, because when we scale by a factor of 2, we're scaling it uniformly, right? Our new shape is going to become something like this, 10 and 4, right? These are similar figures, of course. So when we have similar figures, our area scale factor, it's going to be by a factor of r squared. All right. So using this knowledge, why don't you guys take a moment, if you're in class, I'll probably have you guys work with a neighbor, try to fill in this table using that idea. So this is what we're given. We have a triangle with a base of 3, a height of 4, scale factor 1, we're not doing anything, that's the original triangle. The area of the original triangle is going to be 6 square centimeters, and there we go. So actually, I'll do a couple of these with you. So if we scale it by a factor of 2, the new base is going to be 6 centimeters. Our new height will be 8 centimeters. Our area will be base times height divided by 2. So 6 times 8 over 2 is 48 over 2. That's 24 square centimeters. All right, I'm going to stop writing units after this. And notice we multiplied by 2 here, by 2 here. So our scale factor was 2, but our area scale factor is going to be 2 squared, which is 4. And that's exactly what we see here, to go from 6 to 24. Right? So that's the idea. Given any one piece of these information, you can fill in everything else. All right? So have a go at this. And all right, let's check our work. So if we're going from 4 to 12, we're scaling by a factor of 3. So this will be 9. Scale factor will be 3. And if you want, you can calculate the area. It'll be 9 times 12 divided by 2, which is 54. Or if I scale by a factor of 3, I know my area scale factor is going to be 9. So can I just do 6 times 9? And that is also 54. If I'm just given the area scale factor, well, I know r squared is 100, which means my scale factor for the side lengths, right, is going to be 10, the square root of 100, which means this is 3 times 10. It's going to give me 30. That's 4 times 10. It's going to give me 40. And that's 30 times 40 divided by 2 is 600. And you can see that's 6 times 100. Right, gives me 600. If I'm going to 4.5, well, that means my scale factor is times 1.5. And 4 times 1.5 is 6. So my scale factor is 1.5 or 3/2, which means my area scale factor is going to be 2.25. So the new area is going to be 6 times 2.25. Let me do that real quick. That will be 12, 13.5. All right. Next, scale factor of 4/7. So the base will be 3 times 4/7. That's 12/7. The height will be 4 times 4/7. That's 16/7. I do not want to work out that area. But I know the scale factor is going to be 4 over 7 squared, or 16 over 49. So really, I can just do 6 times 16 over 49. 6 times 16 is 96 over 49 square centimeters. Right? And lastly, I have the original area, I have the new area. So what is my scale factor or area scale factor? Well, that's 216 over 6, right? You always take the image value and you divide it by the original value to get a scale factor. So new over original or image over original. So 216 divided by 6. What is that equal to? I think that is 36. So my area scale factor was 36. Which means this scale factor here is 6, and that means my lengths were 18 and 24. All right. So that is applying this idea. All right. If we're dilating about a point by some scale factor, right, we're going to create similar figures. and our area scale factor is going to be r squared. Cool. So the new stuff for today is what's going to happen to the area when we scale it in perpendicular directions by two different factors of a and b. Right? So earlier on, when we had, let's say, I'll draw a triangle. Let's say, I'm going to keep the same units, base of 12 and height of 6. Right? When we scaled by a factor of 2, we scaled all side lengths by a factor of 2. So when we scaled by a factor of 2, it became something like this, 24 and 12. Right? So the area is going to be multiplied by a factor of r squared, or 4. So the area of this guy is, what is that, 72, that's 36. 36 times 4, the area of this guy would be 144. All right, so these are similar figures. But what if I scaled in the horizontal direction by some scale factor, and I scaled in the vertical direction by another scale factor? So I am not creating a similar figure in this instance. So this is what we're talking about here. So a triangle with a base of 12 and a height of 6 is shown below. So you got a base of 12 and a height of 6. If the triangle is stretched by a factor of 2 vertically and by a factor of 1/3 horizontally, make a sketch of the new triangle and fill in the table below. All right, so I'm going to make a copy of the original triangle. Something like this. Give me a second. Here's that. Boom. And there. All right, so copy. Here's our original triangle. 12 and 6. So what we did is we scaled it vertically by a factor of 2. So hold on, I know I can. So only in the vertical direction. So it's not going to be similar because I'm not scaling everything proportionally. So this will just become twice as high. And that's scaling in a vertical direction. So now this is 12. And this is also 12. And that was just scaling vertically by a factor of 2. If I scale horizontally by a factor of 1/3, well, I'm going to be scaling this way, right? So scaling by a factor more than 1, it's going to get bigger. I'm scaling by 1/3, so it's going to be 1/3 of the length horizontally. So instead of 12, this should shrink down to a length of 4. And this is going to be our new triangle after we scale vertically by, so I'm not going to use the letter R anymore. R is usually reserved if it's a single scale factor that's being applied uniformly in all directions. So let's call this a scale factor of A. Scaled vertically by A equals 2, and then we scaled horizontally by a scale factor of B equals 1/3. And this is what happens when we do that. All right, so our original base was 12. Our new height, our original height, sorry, was 6. So our area is 12 times 6, 72, divided by 2 is 36. I don't care about the units here. So our scale side lengths, we doubled. Sorry, we did not double. What did we do to the base? The base was 12, so that became 4 when we scaled it by a factor of 1/3. And we scaled vertically by a factor of 2, so that becomes 12. And so our new area is 4 times 12 is 48, divided by 2 is 24. So our scale factor here was times 3, and our scale factor here was a half. Sorry, other way around, my bad. Scale factor here was a third, scale factor here was 2, and if you look at the areas, it's 2/3. If we do 24 over 36 to get the area scale factor, all right, 24 over 36, we can divide top and bottom by 12, all right, that's 2/3. And if you notice, when we do 1/3 times 2, that also gives us 2/3. So let's just do this in general. If we had a triangle with some base and some height, right, the original area is going to be base times height over 2. But if we scale vertically by a factor of a, our new height will be a times h. Right, and if we scale horizontally by a factor of b, well, I should probably use a different letter than b. If we scale horizontally by a factor of, let's say, c, actually, whatever, I'll use c. I see, let's make that a c, just to keep it consistent, right? Then our new area is going to be base, which is ch, times height, which is ah. I'm sorry, not ch. That should be a b for base, right? We scaled our base by a factor of c. So we're scaling in 2 perpendicular directions, like vertical direction and horizontal direction, by 2 different scale factors. Right? So our new area will be the base cb times our new height ah divided by 2. And so the area is ac times hb over 2. Or let me keep it consistent, I'm sorry, bh over 2. So if you notice, if you compare our new scaled area to our original area, well, the scale factor for the areas, it's times a factor of AC, or by our 2 scale factors. And that's exactly what we see here. When we scaled by a third in one direction and 2 by another direction, right, we had a overall area scale factor of 1/3 times 2, or 2/3. So when you are scaling by different factors, A and B, in 2 perpendicular directions, I'll talk more about this in a second, the area of the scaled new figure, planar just means 2D, right? It's going to be A times B times the original area. Right, and I'm sorry I changed the B to the C there, just so the base wasn't too confusing, but same idea, just different letter. All right. I want to show you this more on Microsoft Word, because that's actually what I found the easiest to show this in. So I'm going to change the screen I'm sharing. New share. Let's share this. And I'm hoping you guys see my Word now. All right. So let's say we had, or let me do what we were doing before. So we had this triangle, right? The area of this triangle was 36. So what we did is we scaled, again, vertically by a factor of 2, so like that, right? And then we scaled horizontally by a factor of 1/3, like that. So the new area, all we have to do is multiply the original area by 2 and by 1/3, right? By our 2 scale factors. And this is going to be true for any shape, any planar shape, any 2D shape. So take a look. If I draw a random shape like this, all right, let's say the area of this original shape was, I don't know, 50. Just making it up. All right, 50 whatever units. Can I type here, please? Go away. All right, let's say the area of this guy was 50 units squared. So if I take this guy and I scale it horizontally by a factor of 2, only horizontally by a factor of 2, this new area is going to be 100 square units. Right? But then I could also scale it vertically by a different factor. If I scale it vertically by a half, well, guess what? These two areas are going to be the same now because I scaled it horizontally by a factor of 2. And then when I scale it by a factor of half vertically, well, then they kind of cancel each other out. These are going to have the same area. And they actually kind of look to have pretty similar areas. Right? Obviously, I'm not scaling exactly, but hopefully that gives you an idea. All right. So let's go back to that. So that's 100. I just scaled horizontally by a factor of 2. I can also scale vertically by a factor of 2. Right? And when I do that, well, then that's our original case when I scale by the same amount in both directions. In other words, these shapes are similar. So if I scale by a factor of 2 horizontally and vertically, well, the area is going to be, 200 square units, right? Because our scale factor now is just 2, right? It's like a dilation. These are similar figures now. So I can just do 2 squared, or times 4 for the areas to get 200. Right, and what I mean by perpendicular directions is, you notice I'm scaling vertically and horizontally. Right, those are perpendicular directions. And pretty much anytime we scale in 2 different perpendicular directions, it's going to be the vertical direction and horizontal direction, but it doesn't have to be, right? If this were my original shape, it looks like this, right? I could scale this in this direction and this direction. And the same exact principles would apply, right? This could be a scale factor of A in this direction, as long as the other scaling direction is perpendicular to that original, or the first scaling direction, right? This rule is still going to apply. So I'm going to go back to the iPad now, and screen zoom, and hopefully that helped with what we're doing when we said about 2 perpendicular directions. It's a very simple concept. It's just however much we scale in one direction times the amount we scaled in the other perpendicular direction times the original area is going to be the new area of the scaled figure. All right, cool. So let's practice using some of these ideas. So a couple problems down here. All right, in the figure below, AE and, is that supposed to be AE? AE and DE are parallel segments. All right, I'll fix this on your version. This should say AB. All right, AB and DE are parallel. AE and BD, those are straight lines. And therefore, triangle ABC and CDE are similar. How do we know this? Well, pretty simple. If these are parallel, these are alternate interior angles. They already labeled that for us. These would also be alternate interior angles. These are vertical angles. So they're similar. We know this by angle-angle. What is the scale factor of the similarity transformation that takes triangle ABC to CDE? Well, triangle ABC has a length of 11 here. The length in this triangle is the length of 4, and we know those are the corresponding sides. If you want to set up the correct order for the triangles, we could, right? So the scale factor that takes triangle ABC to ABC, this should really say triangle E, right? A corresponds with E, B corresponds with D, so this should say EDC. Want to be correct. So we're going from a bigger triangle to a smaller triangle. And again, the scale factor is always the image over the original, or the new one over the original. So our scale factor in this case is 4/11. Right, and I'm just using the letter R because these are similar figures, right? There's just one scale factor. So what is the value of the ratio of the area of triangle ABC to the area of triangle CDE? Explain how you know this. So the ratio of the areas is going to be R squared, or 16/121. Right, explain how you know. I know this because again, this should really say EDC. I know this because the triangles are similar. So their areas have a scale factor of R squared. All right, so if the area of triangle ABC is 30, what's the area of triangle EDC? And so if that's 30, all I have to do is multiply by 16/121. And that's going to equal 480/121 centimeters squared. All right, you don't even need to simplify the fraction. But if you want, let's see if I can get an exact answer. Yeah, too many decimals, I'll just round it. And that is about 3.967 square centimeters. So it's a lot smaller, right? It went from about 30 to 4. And yes, so that's 30, that's area 4. Looks about right, too, right? But do not give me that answer. Leave your answer as that fraction. All right, number 2, describe 3 different ways one could scale a triangle to change its area from 8 units squared to 32 units squared. So we got a triangle. Any triangle will do. The area is 8. How can we get a triangle with an area of 32? Well, I noticed area of 32 is times 4. So I could scale it by a factor of 4. Sorry, not 4, by a factor of 2, right? So when I scale by a factor of 2, the area will get multiplied by a factor of R squared. So I could scale by a factor of 4. And that's all we need to say. That's one way. Right, but we could also scale horizontally and vertically by different amounts. So for example, I could quadruple that length. So I can scale by a factor of 1, 2, 3, 4. And I could make that 4 times as long. And I could keep everything else the same. Right? So I'm only scaling in one direction. And let's assume this is horizontal. So I can scale in the horizontal direction by a factor of 4. And that's it. Right? Scale horizontally by a factor of 4. Also on number 1 here, I should say scale by a factor of 2. I think I said that, but I wrote 4. Right, because scale by a factor of 2. And if you just say scale by a factor of something, that implies that we're scaling uniformly in all directions by a factor of 2. So you don't need to say scale horizontally and vertically by a factor of 2. Right? But when we say specify horizontally, then we're only scaling in that specified direction. Right? We can also scale vertically by a factor of 4. Right? Just one or the other. We can also scale, horizontally by a factor of whatever we want. I can pick any number, but let's say I picked 8. If I scaled horizontally by a factor of 8, what do I need to scale by vertically? Well, all I have to do is make sure that the two perpendicular scale factors multiply to 4. So if I scale horizontally by 8, that means I need to scale vertically by a factor of a half. And that would also give me an area of 32 square units, right? Because 8 times a half is 4. So overall, I'm multiplying the area by 4. So there's infinitely many ways to do this. You just need to think of two numbers that multiply to that multiply to 4, pretty much. So you can scale by a factor of, I don't know, 4/3 and 1/3, right? You can do horizontally by 4/3 and vertically by, sorry, not 4/3 and 1/3. You can scale horizontally by a factor of 4/3 and vertically by a factor of 3, right? Because 4/3 and 3 multiply to 4 also. And it doesn't have to be horizontal and vertical, just two perpendicular directions. But horizontal and vertical, of course, is the easiest way to do it. All right, number 3, find the ratio of the areas of the similar stars below. The lengths of a corresponding line segment are shown. So the key thing here is that these stars are similar, right? If they are similar, well, the ratio of their side lengths is, again, image over original. So the R value is 7/4, which means the area, the ratio of the areas is going to be 49/16, right? Just R squared. And again, I know that because they're similar. So I'm scaling in all directions by the same amount. All right, and number 4, same idea. Rectangles A and B are similar and drawn to scale. If the area of rectangle A is 88, what is the area of rectangle B? So I'm going to assume these are corresponding sides, even though there's not enough information, but let's assume that. So if these are similar, again, my scale factor is going to be 30/16. And let me actually get this as a decimal, because I think with fractions it's going to be kind of big. So 30/16, that is 1.875. So my ratio for the areas is going to be 1.875 squared, which is 3.515625. So if the area of rectangle A is 88, area of A equals 88, and the area of B is going to be 88 times that number we just found before. Right, area of B is going to equal 88 times R squared. And R squared, of course, is right there. And that ends up being 309.375. And let's include the units, millimeters squared. All right. So really nothing too crazy here, right? If we scaled vertically and horizontally by different scale factors, just multiply those two scale factors together. All right. So that's it. That's the scaling principle for area. There's going to be some trig review questions on the homework. Any questions, just send me a message or an email. All right, so that's it for today. Thank you guys. Hopefully I'll see you guys soon this year. Probably not though, but take care, stay safe, and I'll see you guys later. Oh, I gotta stop the recording from, not here, but